Thank you for the introduction, and thank you all for your time and attention today. Happy to have the opportunity to talk to you about some of the work that we're doing in my group to take major residues from processing of fruits and vegetables in California and upgrade them into value-added products by way of putting them back into the soil, putting them to work for us in agricultural soils to do a number of things to improve soil health. I'll be focusing on a specific technology today called biosolarization. These days it's somewhat synonymously used with another term called anaerobic soil disinfestation. But at its heart, this is a process geared towards disinfesting agricultural soils or eliminating pests and pathogens in agricultural soils. And it does that without any exogenous pesticides. Instead, it uses a combination of solar heating and microbial activity in the soil to create conditions that are hostile to a broad range of pests. And so in this way, it provides an avenue to displace the use of common pesticides, specifically fumigants and herbicides. And so in that way, it can decrease the regulatory burden for conventional growers. It can also be a good option for organic growers where you don't have the same range of fumigants and pesticides available. And then we get some unique benefits that you wouldn't get with a typical pesticide by virtue of adding organic matter to the soil, which is a key component of this whole process. So let me tell you about how we go about biosolarizing soil. It starts with some agricultural soil, could be beds, could just be flat ground. We broadcast some type of organic matter amendment, and then we incorporate that into the soil using tillage or disking. From there, we lay drip line so that we can control the moisture content of the soil, and then we cover with transparent plastic tarp. So all of these steps can be done using common tractor implements. From there, the process is activated by irrigating through the drip line. So as you bring the soil up to its field capacity, a number of things happen. And so from there, it makes sense to talk about this interface between the atmosphere, the tarp, and the soil, and all the different things that we're inducing that help to knock out pests. The first thing that happens is that we have sunlight going through that transparent plastic tarp. It's being absorbed by the soil, and then the soil is radiating out this longer wavelength infrared light, but the properties of the tarp trap that radiation and reflect it back into the soil. And so what you have going on here is essentially a greenhouse effect at the level of the soil. So you've got this accumulation of soil, radiation energy in the soil, and just as you would have heating of your car, parking it out in the sun on a hot day, we have heating of the soil. And that soil heating can be substantial, so we can get to temperatures in excess of 65 degrees centigrade near the surface. And those temperature extremes do a lot to knock out pests on their own. But there's also some other things that happen in the soil. By virtue of the fact that we have this tarp that's preventing oxygen from getting into the soil, and the fact that we've introduced some organic matter into the soil, what it does is it activates certain microbes. And what those microbes do is they become more active, they start to break down and metabolize the organic matter that we've introduced into the soil. But because there's no oxygen diffusing down into the soil because of that tarp, that microbial activity manifests as anaerobic fermentation. And we start to see accumulation of fermentation products. These are things that are typically organic acids, things like acetic acid. And acetic acid is actually what we would call a biopesticide. It's a chemical that is actually effective at inactivating a broad range of soil pests, from weed seeds to nematodes to fungal and bacterial pathogens. But unlike conventional pesticides, they're actually quite safe for people. For instance, we eat acetic acid in the form of vinegar, 5% solution of acetic acid. Another common biopesticide that we accumulate in the soil during this process is propionic acid. If you ever kind of not smelled too good after going to the gym, what you're smelling is propionic acid that's produced by the bacteria on your skin. So it doesn't smell great, but it's safe for human contact. And then another predominant organic acid biopesticide that we see is butyric acid. This is something that you have in your stomach acid right now. So again, very safe relative to conventional soil fumigants, some of which before being used in agriculture were used for chemical warfare and clearing trenches in World War I, for example. So that's how biosolarization works, and we wanted to see if we could use biosolarization as an avenue to add value to a major solid organic waste stream in California. This is something called tomato pumice. California produces virtually all of the nation's processing tomatoes, and most of those go into producing tomato paste. When you make tomato paste, you're separating the juice from the skins and seeds, and those skins and seeds are what we call pumice. So there are hundreds of thousands of tons of tomato pumice in California produced each year, typically routed into animal feed outlets, but we wanted to see if we could provide a new kind of closed-loop recycling strategy by putting this material back into California agriculture. So what we did is take samples of tomato pumice from Central Valley processing facilities, and then we amended it into agricultural soil samples. So looking at varying levels of tomato pumice in the soil, and then we also looked at certain scenarios where compost was added as a co-amendment, the rationale there being that the tomato pumice is food for the soil microbes, and then the compost is a way to kind of kickstart that microbial community by just inoculating it with microbes that are already very well adapted to breaking down plant biomass and fermenting under high temperature conditions. And we compared these amended soils to just a control, which was non-amended, untreated soil. And we test this using a field trial approach. And so we create biosolarized plots, and then buried within those soils we have these mesocosms, which are essentially soil bags that contain samples of the different amended soils. And embedded within that are these satchels that have a porous mesh in which we've embedded different pests and pathogens. Could be weed seeds, could be fungal pathogens, but they allow us to retrieve a controlled volume of that from the field. And so here is an example of what a research biosolarization plot might look like. These are prepared by our team down at the Kearney Ag Station near Fresno. And so we biosolarized for 8 days, and then looked to see how different pests were inactivated in the soil over that time. One thing that we looked at was an activation of seeds from Brassica nigra. This is commonly known as black mustard. It's the same mustard you might grow as a spice, but it also grows globally as a weed. And it actually produces allelopathic compounds. These are chemicals that actually prevent other plants from growing, and so it can actually be a destructive agricultural weed. What we saw here is that in the control scenarios where you have untreated soil or soil that's only been heated or only contains the amendment without heating, we don't see any significant increase in seed inactivation compared to that negative control. But when you combine, in the context of biosolarization, the solar heating and the fermentation of the amendment, we do see complete inactivation of the weed by the end of that 8-day treatment period. We also looked at another herbaceous weed. This is black nightshade, Solanum nigrum, another major California weed. In addition to competing with crops, it can also harbor pests and pathogens that further harm the crop. Similar trend here in terms of if you decouple the heating and the fermentation, there's no benefit to seed inactivation compared to the untreated case. But you do get this synergistic activity when you have those two stresses together, and again, complete inactivation of the weeds by the 8-day treatment period. So going beyond plant pests, we also looked at control of fungal pathogens. We had a fusarium infestation in this field plot. And fusarium is a fungal pathogen that is globally relevant, causes wilt and rot on hundreds of different crops, spanning grains to fresh fruits, tree nuts. Here's an example of corn with ear rot caused by gibberella, and gibberella is just the teleomorph of fusarium. It's the sexual reproductive stage of that fungus. So we looked to see how fusarium levels were changing in the soil using DNA sequencing and bioinformatics approaches. What we have here are some plots that show the initial relative abundance of fusarium in our different amendment treatments, and then looking to see how those levels change under a room temperature incubation. And you can see, for instance, for this treatment, which is the pumice with the compost, even the amendment alone acted to decrease the level of fusarium. If you look at solarization, which is just solar heating by itself, no amendment, no significant change in the fusarium levels across our different depth levels. This is down to 2.5 inches, 5 inches, and 7.5 inches depth. But then when you get to biosolarization, it's really this combination of the solar heating and the amendment with both the tomato pumice and that compost inoculum that led to a significant decrease in the relative abundance of the pathogen across all the different depth layers that we observed. Looking at gibberella, the teleomorph, same type of trend here, high levels initially in the soil. In this case, solarization or solar heating did inactivate some of those pathogens, particularly in the upper layer that gets the hottest. But again, in biosolarization, it's this unique combination of the solar heating and the amendment with both the pumice and the compost that led to high-level control across all the depths tested. So clearly this technology can be very effective at knocking out a broad variety of different pests. One thing we want to guard against is making sure it's not so good at killing things that it also harms the crop that we plant subsequently. We'd like to deliver a benefit to crop yield by virtue of eliminating the pests. So what we did is take samples from those field plots, bring them to the greenhouse, and use them to grow tomatoes. We took them to harvest, and we repeated this in 2 years. Both years showed high levels of pest inactivation. In the 2015 trial, we knocked out the pests, but it didn't significantly affect the growth of the tomatoes either way. In 2016, we did see a marked increase in the amount and mass of fruit for the plants grown in the biosolarized soils. So the difference between 2015 and 2016 really highlights the importance of remediating the soils after you biosolarize them. In 2015, we had a 7-day remediation, meaning it was 7 days from when we pulled the tarps off to when we planted the tomato transplants. But in 2016, it was 2 weeks, so an extra 7 days, allowing those biopesticides to break down and dissipate and completely dissipate from the soil. And once you get rid of those residual biopesticides, then the fertility benefits to the soil shine through. So it's not just about knocking out the pests, it's about remediating the soil, getting rid of those active compounds before you introduce your crop. So in terms of the technical efficacy, biosolarization is promising. It sounds like it should be sustainable because we're taking these waste streams and putting them back into agriculture, but we wanted to try to answer that quantitatively. And so we had the question of whether biosolarization is more sustainable than the business as usual approach of fumigating the soil. And we examined this question through the lens of life cycle assessment. So we asked if we took the tomato pumice from all tomato processing facilities in California, and there's about 23 facilities that are responsible for all tomato processing in California and by extension the United States. What if we routed all of that pumice into biosolarization? And what if we did that in an area that is well suited for biosolarization? Someplace like Fresno County, where there's currently a lot of fumigation, and the types of crops and seasonality of those crops lend themselves well to the timing of biosolarization. What if we compared that scenario to something a little more conventional, which would be just routing the pumice into an animal feed application. What if we did that in a similar region, something like Tulare County, where there's a lot of dairy farms, and tomato pumice is known to be an excellent addition to a feed ration on a dairy farm. So between these two scenarios, we basically have one where we're displacing some fumigation by putting the tomato pumice into biosolarization. In that case, we're kind of robbing the dairy farmers of their pumice. They're going to have to source some alternative feed to make up for that, and comparing that to the business as usual scenario where fumigation is used for pest inactivation in the soil and the tomato pumice is routed for feed application. So without going too much into all of the LCA nuance, we took inventory of all the different material and energy inputs that are needed to do biosolarization, to do fumigation, to source and deliver feed to these locations, and look to see how much global warming potential was embedded in each one of those inputs, represented as the amount of carbon emissions that you would have. So here are the results of that LCA. Looking at global warming potential, we see that there's roughly a 20% decrease in carbon emissions expected for the biosolarization scenario, where we're taking the pumice away from the dairy farmers, putting it back into the soil. The dairy farmers are getting alternative feeds to make up for that deficit, compared to the business as usual approach of fumigating the fields and using the pumice as feed. And that decrease in carbon emissions is concurrent with a decrease in the total energy input, known as the primary energy demand, to conduct biosolarization versus conventional fumigation. So we can say, based on this assessment, quantitatively, biosolarization is predicted to be more sustainable than the current practices based on a reduction in greenhouse gas emissions. Those reductions come from predominantly one effect. So these are charts that show how different elements of each scenario contribute to the overall carbon footprint. Both scenarios have a large footprint from plastic production. In fact, the same plastic that you would lay over soil to fumigate it is identical to that we use for biosolarization. So there's the same amount of embedded emissions for producing and transporting that plastic. We found that there's a similar impact of using pumice for animal feed versus sourcing some alternative feed to make up for pumice that's being routed into biosolarization. Some unique elements to each scenario. For instance, in biosolarization, we have an irrigation step. You recall that we laid that drip line. We had to irrigate the soil to activate all of these microbial processes. You don't irrigate when you fumigate soil, so that's a unique element here. And so the material inputs, the fuel energy needed to lay the drip line are unique to that scenario. And then unique to the fumigation scenarios, the use of the fumigant. So all of the emissions associated with mining the raw materials, processing them into the fumigant, packaging them, transporting them to California, substantial fraction of the overall carbon footprint for that scenario. And then here we have pumice transport to these agricultural fields instead of the dairy farms, another unique element up here. So it's basically elimination of the fumigant production aspect that affords the net decrease in carbon emissions. That is just such a prominent factor in terms of the energy and emissions associated with making those materials, and a lot of them are produced in Texas, and then bringing them to California, as opposed to using these locally produced, if you want to think of it that way, waste streams, because these tomato processing facilities are basically adjacent to fields that could use this technology. So I focused on tomato pumice as an example of how we can take a predominant waste stream and look at a number of different angles of how it's used in biosolarization, but I want to give you just a taste of some of the other streams that we're working with as well. Grape pumice from wine production. These are the skins and seeds that are left over after you press the grapes. And we're looking at this in biosolarization. to specifically control human pathogens in agricultural soils. So those grape skins contain a lot of different phenolic compounds that are known to be antimicrobial. Can we put these into the soil in biosolarization and capitalize on those compounds to knock out human pathogens in the soil and benefit food safety during the agricultural stage? So here are some data showing that you can get a 5-log reduction in soil E. coli using biosolarization with grape pomace. And again, this is a synergistic effect. So it is much higher than what you would get if you just solarized or used solar heating alone with no amendments, or if you just put the grape pomace into the soil but don't solar heat it. So like we saw with the tomato pomace, it's the synergistic action of those stresses that's really effective in knocking out this pathogen. We also look at residues from almond processing. So most of what you harvest from an almond tree is not what you eat. Most of the biomass exists as this mixture of hulls and shells. The hulls are a very leathery, fibrous material. The shells are a very woody, fibrous material. And so we also looked to see if we could use those in the context of biosolarization. And in this study, we were specifically looking to see if we could knock out soil nematodes. These are small worm-like creatures that a certain class of them can infest roots, cause nodules and lesions that harm the plant. And so we found that these materials are actually very nematocidal. They're very good at knocking out these phytoparasitic nematodes. This is showing extracts from biosolarized soils that contain these almond residues. What we saw is that even if you don't allow them to ferment in the soil, if you just put the hulls and shells into the soil is immediately nematocidal. Actually, there's endogenous organic acid and flavonoid biopesticides within the hulls that act immediately. But if you do allow them to ferment in the soil after 8 days, for instance, you can enhance the amount of organic acids that are there, and you improve the inactivation kinetics of those soils. So when we exposed nematodes, root lesion nematode, to these extracts, they were dead in a matter of hours completely. So highly nematocidal. So with the support of the Almond Board, we took this and scaled it out to a field trial. This is actually our largest field trial to date, a 10-acre trial up in Chico with a commercial grower. And this is production acreage. So we conducted this back in 2017. The trees were planted, and we're tracking the performance of those trees. First harvest should be next season, in fact. So stay tuned for that one, but just showing you how we can take this technology and aim it at different waste streams and different crops within California. And so, all this happens with a very productive collaboration across UC Davis, other universities, and with cooperative extension as well. And I just want to acknowledge their valuable input here, as well as the valued sponsorship that we've received from federal, state, and private sources. And thank you all for your attention today.